Okay, we've got this fancy Delancey real-time closed captioning, which Carthage has added to our Zoom account. And it works pretty well. It makes a lot of mistakes. And also it's always in the way of whatever it is that I want to see on screen, just like a lot of other parts of Zoom's UI. Excuse me for 1 second. Okay, so the agenda for today, go away, puppy. I have a puppy. Let's see, share screen. Okay. The agenda for today is, of course, review, project questions, there's project 4 to introduce, and I have rewritten another explainer program for Float, and I really think you're going to totally get it. Everything there is to know about floats when you see this program run. And also, we will review Union. But the second version of the program uses a completely different technique known as bit fields. And I am betting that students are generally not aware of how to use bit fields. Okay. Let's see, and other floating point matters. Okay, how about some questions? Go ahead. No one has any questions. How do I?
I'm pretty sure we have questions. We just don't know how to articulate them.
Okay. Step 1, think. Step 2, talk. For everyone else, step 3, snicker. Go ahead. Okay, you are welcome to resubmit projects 1, 2, and 3. I have been regrading for many of you, and there are some people who have not turned in work. I suggest you do it. No questions.
I guess I have a question, like how long are you gonna be regrading like project 3?
How long before you turn it in?
All right.
Okay, now I can't guarantee forever, but I'm being pretty open.
I think one of the biggest questions I have is, like, in project 3, when you are wanting to read from your intermediate buffer to the final buffer that's going to hold the string, is there like an easy way to do that, or do we have to go letter by letter, or char by char, I should say?
Well, the easy way to do it is to call somebody else's function that's already written, and you'll find strcpy, which is out of favor. strcpy, and that is out of favor versus strncpy. And both of these have the same first 2 arguments, the destination, the source. This one has destination, source, and count. Okay, so you could make use of somebody else's. Or
what do you mean by out of favor?
strcpy is in some systems deprecated. While it still is recognized, it won't allow you to use it. The reason being is strcpy depends upon there being null terminated strings. So it also depends upon having buffers that are already big enough. The more modern strncpy accomplishes the same thing, but adds the count field, which limits the number of characters copied. So using strncpy, you are less likely to write a buffer overflow because you control the maximum number of characters to be transferred.
I have a review question.
Okay, now just to finish up with Jordan's question, or you could write your own. Yeah, go ahead.
So when you're using the count, essentially, because you would keep track of how many chars are entered in, you would have both a new line char, and then after the new line char is the null terminating char. Is the null terminating char included in the count from the initial character, or is it only up to the new line?
It's up to the new line. If you were to use strlen, give it a char pointer, that would return the number of non-null bytes. So it would include the new line.
Everything but the null terminator, yeah.
Correct, right.
Okay.
Right.
So I just want to confirm, when you're reading in the line, once you get to a new line, you want to not read the new line and cut it off there. And then when you are reading that over to str copy, you want a null terminator at the end of that. Right?
Correct, right.
Okay.
So, but you said something that was odd, and that is you don't want to read the new line. You already did.
Yeah.
You just don't want to transfer the new line.
Yeah.
Right. So, if you go ahead.
One review question I was thinking, I'm still a little bit confused with two's complement. So could we go over that again real quick at a time?
Sure, I'll add that. Okay. Okay, go ahead.
I have a general question. I've been trying to find a reliable website where it.
He froze. Hello.
Sorry, yeah, somebody just called me, so it kicked me out for a second. So I've been trying to find a website that has the system function calls, as in like memset, malloc. Obviously, I know some of them already, but I just wanted, like, do you know of a website that has them all in a centralized place? Because the ARM architecture documents, they have some functions that involve registers, but they don't really have like the BL with the linked return calls. It doesn't have really a directory of what is available to use. Because I was looking if there was an int to ASCII. I know there isn't. I got through that, but yeah, just in general, I would like to find somewhere where I can look at all the function calls.
Right. Well, but you asked me two questions though. You said function calls and ARM assembly language. So which is it?
Oh, no, I said the ARM assembly language architecture has reference to like load, store, different things with registers, but it doesn't have the call and return titles such as malloc, etc. Free.
Okay, good. Well, yes. There are websites that have everything in one centralized place. CPP reference, for example, also has a C reference and the websites like that. I'm going to pull up a CPP reference, and I'll take a look.
For
All right.
actual Linux syscalls, there's something about dice. It's like DEI or something. It's like an online version of the man pages, I think.
Well, you all have the man pages on your computers. So here is, and we'll look at that. So, yeah, I want to go over this for you too. So, headers. So take a look at, for example, stdlib, memory management, program utilities, string conversions, random numbers, and algorithms. Okay. String, we'll have some of the ones that I just talked to Jordan about. For example, click here. And here's A to I.
But these aren't actually syscalls. These are C
are
functions.
Yes, that's correct. Yes. So there is a difference between these and an actual system call. Definition of a system call is something that is implemented by the operating system. And when you make the call, there is a transition from user space to kernel space, kernel being the operating system. These, however, are not system calls. They are part of the standard runtime library, RTL. C standard runtime library is pretty much standard everywhere you go. Right? You'll note that some of these note that which version of C they became part of. However, you're using assembly language, so I wouldn't be surprised if all of them work. We haven't gotten to 2023 yet, so I wonder how that's there. But who cares? All right, now you all have man pages, every single one of you. Let's see, I believe that I have already launched. What the heck? Oh, well.
You're still on.
I know.
Okay.
Okay, so so man, strlen. There's your man page. Okay, the 3 over here says chapter 3 of the manual. Now, speaking of the manual, when I was learning this, I had a printed copy of the entire manual. In fact, I still have it. Came across it just the other day. And I read it page to page. I read every goddamn page in the manuals that come with Unix. And I expect you to too. You should do that as well. That's not an unreasonable request. You're in charge of your own careers, and in part of your career, you have some tool sets that you have to work with, and it's incumbent upon you to be masters of those tool sets. Period. Chapter 1 are shell commands. In the Unix manuals, chapter 1 is shell commands. Chapter 2 is system calls. Chapter 3, runtime library calls. Okay, so for example, if I say man read, that is the shell command that's a built-in. So let's say man to read. There's the system call from chapter 2. Sometimes you'll get a name collision between more than one chapter, so you can specify which chapter you're looking for. First chapter is shell commands. Second chapter, system calls. Third chapter, runtime library calls. There are 7 chapters.
That's a pretty speedy index they've got there.
Yep, yep. Okay, so this is available on you're not looking at my virtual machine, but it is available on your virtual machine. So let me start up the virtual machine because we got lots to look at. So there. And give me another tab and another tab. But you can't see the tabs that I just switched to. Okay, so. All right, does that work any better? Yep. Okay, so I want to show you this absolutely gorgeous. I was so pleased with this. It's a little ditty and it's just elegant and I love it. So I'm going to show you this new version of the program that I wrote to visualize floating point numbers. And let me first find where to point you for you to get the source code. So if you look at Schoology, you'll find under reference material a float.cpp. Okay, so you can download that and just gaze at its magical goodness. Okay, so I might as well download a copy of that. And let me go back to the terminal. And what did I, let me go see what it is that I downloaded. Come on, fingers. All right, so let's say code float CPP. And where is my button? Okay, code. All right. So if I make this smaller, it'll be bigger. It's one of the things, you know, Einstein's relativity is at play here. Okay, look. I have shown you unions before. So what I did last time is I created a union and then did bit bashing. Okay, so there was a union between a float and an int, right? And so I loaded a float into the F portion of the union, and then I examined bits using the I portion of the union. That was union float F int I. Actually, it was unsigned int I. Okay. And the bit bashing that I did was things like anding and shifting. We're going to study bit bashing on its own, but not today. Okay, what I'm showing you today is a different approach called bit fields. And here is a struct which has 3 members in it. They're all declared as unsigned ints. But what are their sizes? You may have never seen this syntax before. Unsigned int, and then a name, and then a colon. All right, how many people have seen that? Okay.
No try.
All right. So these sizes here are defined above. We have 1 bit for sign, 8 bits for exponent, and 23 bits for fraction. These numbers should be familiar to you because you're all experts on floating point now. But take a look down here. I'm saying that the fractional part is an unsigned 23-bit number. Expo is an 8-bit number and sign is a 1-bit number. Tom, did you have a question?
I was going to ask, what if we aren't an expert in how floats work?
That's what this program will teach you because it's just so clear. It's beautiful, beautiful program. So here's what I did. You took this structure that has bit fields and I unioned that with a float. The advantage of bit fields versus the bit bashing is that the compiler generates the bit bashing instead of you having to generate the bit bashing. Okay, so for instance, in the other program where you had to do the bit bashing manually, to get the sign, you would test bit 31 by shifting it down 30 places. Bit 31 by 31 places and looking at the least significant bit. Here, you can actually leverage the sign bit as a normal variable. And underneath the hood, the compiler has generated the bit bashing to isolate the 1-bit sign so that you don't have to. Okay, so let's compile this program and watch it work. And where am I? I'm in the downloads. Okay. Okay, so this will use, instead of asking for input, it uses the command line. And so how about a 1? And check this out. So the float that was entered was 1. It's positive, so that the sign is a 0. The exponent is 7f, which is 127. So if you subtract 127 from 127, you get an exponent of 0. The fractional part is 0, and then I wrap it all up together for you. The value of 1 is expressed as a floating point value as 1 times 2 to the 0. Let's try something more complicated. 1.5, then that's all we'll do. Okay, so what I entered was 1.5. Notice the exponent is the same. And the 400,000 hex here is the fractional part, and that converts to 0.5. If you want to take a look, how did I convert the binary to a floating point fraction? That's here. I'm examining each bit in the fraction only. And based upon its bit position, the divisor changes. So I just did 1.5, so that was the most significant bit, was turned on in the fraction. So that'll be 1/2. That makes 0.5. All right, let's do something more complicated. Let's do, I don't know, -1.5. What is the difference? The difference in output is only in the sign bit. 1.5, -1.5. What if we were to do, let's say, 16? That's only going to change the, well, that's going to change the exponent. What's 2 to the 4th? 16. Well, how about 16.125, which, by the way, is a fractional power of 2. Okay. So I didn't get 1.125 here. Here, watch. If I do this, 1.125, the fractional part is literally the 125. But if it was 16, then you have to take into account that the power that you're raising 2 by is larger than 0. So what is this number times 16? That's how you get to 16.125. All right, so pick a number. Anybody have a particular number they want to see visualized?
84.
There up by the thing.
Okay, keep going.
It's
3.1415.
there's a grass-fed all beef.
Is that right?
3.14159, I believe.
Yeah. 42.001.
Okay, so let's take a look. I put in 84 and I got 84. So it's 2 to the 6th times 1.3125. Okay.
Could
Now
you
this, yeah,
briefly review, like taking a look at specifically the fraction hex? How do we like interpret that to, like in this case, how do we know to read 0x280000 as 0.3125?
got it coming up. All right. So we just had 280000. Is that correct? I'm not looking at it.
I believe so.
Correct. Okay. So let's convert this from hexadecimal to binary. I'll start on the right-hand side. There's 3 zeros, so that makes 12 zeros in binary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's why we use hexadecimal, because it's shorter. Okay, now there's this 0. That's another 4 zeros. And then there's an 8, which is 1, 0, 0, 0. And then there's a 2. That's 1, 0. Okay. Now I've just taken the 2 8 zeros and converted it to binary. Now let's interpret it as a fraction. So this is the halves. This is the quarters. This is the eighths. This is the 16ths. These are the 32nds, 64, 128, etc. So what is a half plus an eighth? That's
Be
5
5/8.
eighths. Huh? What's that?
I was answering your question. I'm sorry.
Yep, 5 eighths, which is what? 65. Let's take a look at the number that we were trying to do. So 3125. So did I get one wrong? Oh, yeah, okay, I did get one wrong. Right. So there's another 0 here. Let's see, this is supposed to be 4 digits and I only wrote 2. Okay, so let me erase and we'll just do a quick calculation again. So this is the halves, this is the quarters, this is an eighth.
You're still showing the other screen.
Yeah, well, doing what I do, this is why I get paid the big bucks, right? It's a complicated process. Anyway, where I went wrong before is this was not the most significant bit. So if you put this together here, that's the 2. So I started counting from the wrong place. So 0 halves, 0 quarters, 1/8, and that is the 16th, and then that is 30 seconds. So it's an 1/8 plus a 32nd. All right. So now you can see how is it that a floating point number is put together. Especially helpful, I think, is this line down here.
I have a quick question.
Yeah.
So you were saying that the 125 show the decimal place 125 shows up as a 125 when there's an exponent of 1. But when there's not an exponent of 1, it is affected by that because it has to do with that other whole number that it's being multiplied against. So is there a portion of deciding the fraction bits based on what your exponent already is because they're
Yes.
permanent on each other?
Right.
Okay. Well,
Right.
what can I ask then? What is that determinant factor that you would use the exponent in the fraction?
Well, it's log base 2.
Okay.
So log base 2 would give you the exponent and the fraction.
Okay.
So think about it.
Dr.
There's-
Kovalowitz,
Yeah.
our previous
Gotcha.
calculation is off by a professor. It's off by a factor of 2.
All right. So I got a bit wrong somewhere again, but
Isn't the 2 0 1 0 0?
What?
no.
0? Because the thing we calculated is 0.15625, but we want that times 2, which is 0.3125.
Okay.
Yeah, not sure where you went wrong though.
Okay. Well, let's count bits. Let's see. So it's 23 bits. So maybe okay. So this one's not here. Let's calculate
You're
it now, Cephas.
showing the wrong screen.
Right. Let's calculate it now. All right. So if this was well, how many bits do we have here? Here's 4, 8, 12, 16, 20. And so this should be in 3 bits. I had an extra 0. So what would it be now? So 0 halves, 1 quarter, 0 eighths, and 1, what, 16th? Does that come out right now?
Oh, it
Yeah.
should be a single bit shift to the left. And I think that's right.
Yeah, okay, I got it now.
Oh, no, I lied. Yeah, that's it.
Okay. So it shows you the difference between 1 bit and not, okay? So going back to the program. So if we stay with exponent of 0, then the bits are apparent. So here at 1.125, the fractional portion is 125. That only works because the exponent is 0.
Real quick, so why is it 3 bits instead of 4 for the 2 and when we were doing the calculations?
That comes here. You see, it's 23 bits.
Okay, maybe bits was the wrong term. So for binary, you put down 0, 1, 0, right? Why isn't it in like sizes of 4? Why or 2? Like why is it 0, 1, 0, not 1, 0?
That has to do with this 23 that's on screen here,
Oh, okay.
right? So,
Oh, I get it now. Okay, I see.
okay. So there are 5 full hex digits. So that would be 20 bits. And then the most significant, all 4 bits are not being used, only 3 bits. And that's where I went wrong, but that's the nature of your question, right? That's the source of your question.
Yeah, that was.
Right.
Is this float
Okay.
CPP on the GitHub?
Is this what?
Is this float CPP on the GitHub?
Currently, it's on your Schoology.
Okay. I just want to play around with it later so I can get a better understanding of how it's broken down.
Tell you what, why not convert it to use double precision?
That's an idea.
Yep. It's on your Schoology, and so going back here, let's see, are there any other lessons to learn from this code? Rather than using magic numbers of like 23, I made a symbol out of it, so I like that. The cool idea of first creating a struct that is bit fields, and then using the struct in a union. So here I'm converting the fraction from binary into decimal. Okay, is there anything else that's interesting here? Not so much. But as I said, I took a lot of pleasure out of writing this because at the very least, you can see how it works at the end. Namely, this line here is very instructional. I do want to show something though. Let's see. A.out was 0.1. You notice anything strange?
You bias to -4.
Okay.
That's weird.
So 1.6 times 2 to the -4.
Oh, well, that makes sense.
All right. Now, what's interesting though is I typed in 0.1 and without any processing at all, it was interpreted as 0.10000, number of zeros, 149. Here's another example where floats are approximations. Okay. So the closest a single precision number can get to 0.1 is 0.1 with those zeros and 149. Well, Well, okay, well, how about 0.2? How well do we do there? Well, we got a little bit of an issue there. How about 2.5? Well, that one we can hit exactly. Okay, we can't hit 0.26 exactly. We can come this close. Okay, I'm hoping this totally clears up, totally explains how floating point numbers are put together. Very pleased. Couldn't sleep, and this is what came out of it.
You did a great job.
Oh, thank you.
So is the predictor of the accuracy whether it is a natural factor of 2?
Yes, I'm not quite, that sounds good. I'm not quite sure what you mean by natural factor, but it sounds good.
That's not very, it's not a good judgment of correctitude, is it though? Like,
Well,
0.25 is if you divide 1 by 2 times 2, you get 0.25. Which, and it could do that easily.
Right.
But 0.26, you can't.
Right. So what it is can the number be constructed as the sum of powers of 2? And if so, you get an exact value. If not, you get an approximation. Sound good?
Nice.
Okay, good. Any other questions?
What if you put in 0.26, but then also put in the remaining 8 digits as zeros? Would it be able to understand that more precisely as a single precision, or would you still need to use double precision?
Let's try that. So I'm just going to copy here. And I think this is, what the hell does that mean? I don't know what that means. So this is of itself an approximation because there's probably some rounding at the last digit, but let's see how it comes out. Yeah, looks like it was reproduced. Yep, all the digits are there. So
That
there's
wasn't
no
really my
round.
question. Sorry.
Oh, sorry.
What I was saying is you input the 0.26, but then for the 999990463, so that's I think 7 digits. If you put all zeros for them, would it be more precise, or would it still have the same issues with approximating?
Okay,
Or I
if you
guess
had all,
I guess it would, because it's still made up of the sum of the power, the sum of the exponent of 2 and the fraction. I guess it would still have the same issues.
right. Well, if we put in just 2.5, that would be exact.
But yeah, well, it would always have that issue with the 0.26 because of the way it's calculated. Okay.
Right.
Yeah, that makes sense.
Okay. Now the next question is going over 2's complement. So let me switch over to the iPad. So 2's complement. All right, so what you do is you negate the bits, then add 1. Okay, so what is the bitwise negate operator in C and C++? All right, what's the logical negate operator?
Exclamation point, right?
Yes, that's logical
Yeah, logical.
negate. So that will turn something that is non-zero into zero, or zero into non-zero. Is that. But just like there are different operators for logical and bitwise and or, there is a bitwise negate is tilde.
Approximately.
What, that's not a tilde?
No, it's just, it was a joke because like the tilde is always used as like approximately something.
Yeah. Well, okay. So if you had an 8-bit number, because I want to make it easy on me, your 8-bit number, and it was a value of 1, looks like that. That's 1 in 8 bits. The first step is to negate the bits. And then the second step is to add 1. And you get, okay, or F. So there's -1 in 8 bits. Now, does this work to turn it into a positive number again? Let's find out. Take these bits and negate them and add 1. You got your original back. Okay. And if you were to add -1 to +1, you'll get 0. I'll just do the only the least significant 4 bits. So here's the least significant 4 bits of -1 and the least significant 4 bits of +1. No, I did that wrong. There. Okay. So 1 plus 1 is 0 with a carry, 0 with a carry, 0 with a carry, 0. So -1 plus 1 is 0. Amanda, was that, okay, no, that wasn't, it was Rebecca. Does that do it for you for 2's complement?
Yeah, I just needed that overview because I was still a little shaky on it and I wanted to be sure.
Okay. Yeah, good, good. Let me expand this explanation with just one more item, which is, what is 1's complement? And how do you get from 1's complement to 2's complement? Well, after doing this, you've got 1's complement. And when you do the add, now you've got 2's complement.
So I guess I'm kind of confused why you would use 2's complement over 1's complement. Like, wouldn't negating it just do the same thing pretty much? Or not, I mean, -1. Wouldn't negating it give you the opposite value?
Well, let's try using just 4 bits. So if I had 1, 1, and 0, so that's the negation of a 1. And now let me add +1. I get the wrong answer. That's not 0.
Okay, that makes sense.
Yeah, for my hardware shenanigans course, 2's complement is much easier to deal with in the actual hardware because it's essentially the same thing as normal add and stuff, and you just get the value, and it's Gucci. You don't have to do any special case shenanigans.
Yep. And that's part of why we use it. right? That's part of why we use it, and the initial impetus for having this alternate representation of negative numbers is because we didn't want to have two values for 0. All right. So I'd like to move on to the next project. That would be here. And so
I know I
projects.
said this last time, but this one really doesn't seem that difficult. Maybe it's just me. It's like you just
I think it might just be you.
you just have to convert right C in assembly.
Yeah, and I
There are
even
probably
give you the
some
C.
hiccups here and there,
I
but
give you the C.
I'm pretty good at converting
Okay, that
C to
might
assembly.
cut down on some of the time. Yeah.
Mm-hmm. Okay, so here's a program. Let me first show you what it does, and then we'll talk about how it's put together. Could you mute Cephas? Thank you. Let's see. So I need a terminal window, and where are we? Let's see. Go to. Okay, I'm showing the right thing. And go to the projects. This is P4, right? Yeah, okay. So I'm going to compile. What the hell, I'll even optimize it, although that doesn't matter. So the way that you get this to build is you have to add the curses library. Make sure you have the curses library, which I'm pretty sure I already pre-installed. We'll get to that in a minute. So -L link with n curses. Okay. All right, let's run it. Okay, now this looks pretty difficult to tell what's going on. It's because it's going so fast. So here's what I'm going to do. I'm going to make the window bigger. And now I'm going to decrease the font size. All right, and make the window bigger. Okay, let me decrease the font size a lot. Okay, so you're getting a sine wave. An animated sine wave. I don't know.
Could you change the delta T? The tick
Can I
time, whatever.
Can I change the delta T?
Yeah. Don't you do
Sure.
like a timer wait or some sort of wait function?
Right, but I didn't want to have you have to figure out how to do that on the ARM. So what I'm doing instead, I'm doing the next best thing by just slowing it down by having it print more characters.
Oh, is there no not terrible way to?
I was going to ask you to carry this basket, but I don't think you can.
That's pretty slow now, isn't it?
Poor thing.
It's stripey.
Okay, yeah, this is just a little bit too much, I think.
I think this is hilarious. This is great.
Why?
I just think of all the things I was expecting Project 4 to be when I went to class today, I don't know if I expected this. That's why I think it's fun.
Okay.
Is there no way to elegantly pause for time?
No, putting in a delay was more complexity than I wanted. Okay.
All right.
Now, the alternatives to this, I also have a version I could have assigned, which was to produce Julia sets. And also, we could do a version that actually plays movies.
The Julia set one sounds way more fun.
Yeah.
I feel like we should talk about the movie idea in class so we can get exposure to end curses.
Okay, it's the same idea, except you instead of a sine wave, it's the individual frames from a movie. There, actually, maybe I think I can show you that quick, actually. I'll just show it to you because it's fun, it's funny, but I'm gonna not assign it. So let's see, okay. What's in old? If I can't find it real fast, I'll give up. Where would it be? Yeah, I can't find it right now. So, but anyway, yeah, you would feed it an MP4 video file, and it'll play the video in the terminal.
Can you, I mean, like, after the project at least, could you give us the code so like we could show it off to people and be like, hey, look what I did for class and impress people?
Okay, well, I could do that.
Wait. But you didn't do it.
Uh,
Unless you did.
Well, they don't know that. So I'm showing it off to like incoming freshmen or whatever, be like, hey, look what you're going to do in your major.
oh, you know what? I think I have an easy way to find it. So find dot dash print rep MP4. There it is in the dice histogram folder. Okay. I wonder why. I don't know. Where am I going? Dice histogram Python. Oh, this can't be right. Dice histogram. No, the program's not there. Oh, there it is. ASCII art. That makes a lot more sense. All right, let's see what we got here. Python 3 AAV2. I don't know what V2 is. Okay, there's Blazing Saddles.
Beautiful. Absolutely beautiful.
This is the part where they're interviewing gangsters to go rob Rock Ridge. Not rob, but destroy.
Don't forget, they need to pay the toll. They got to get a ton of dimes.
Right.
So like,
So now what's fun about this is if I'm sorry, go ahead and ask your question.
so I'm just curious, like how you would actually code that. Would you look at like each individual pixel and then determine the darkness per se of it and then print out a character in that spot?
Yes, that's exactly what you're doing in Project 4.
Ooh.
Let's make this really small. Okay, a lot of characters, which means, by the way, you'll get a lot of detail. But it slows down. That really does look like the movie. You can even read the sign.
That is so cool.
I definitely can't read that sign.
Register here.
I thought it said Rowdy Boys for a
Hoorah.
second, though I have seen the movie.
Huh.
Chewing gum online. That's about to be said. Okay. Anyway, but that is what you are doing in Project 4.
Although you made this one in Python, which is kind of
Yeah.
cheating, if you ask
That
me.
is so cheating. I mean, how do you do that in assembly?
It's not hard.
I challenge you.
So, Now, let me get back to, all right. So here's the C source code. Here is your palette. See? So something that's dark will be rendered as a space. Let's see, is it? Okay, so something that's dark will be rendered as a space, and something that's bright will be rendered as the @ sign. Now, let me teach you how to use cursive. Okay, so the first thing that you have to do with cursives is called init screen. This is very little of curses. So init screen, then clearly this erases the screen. Then you're going to move to a particular screen location and add a character. And at the end of one screen, you draw a box around it, then call refresh. So there is a 5-second introduction to curses. Now, you may be wondering about sinner, tinner, and binner. C doesn't give you temporary labels, right? So that would be 1, 2, et cetera, et cetera. So this is all, de-evolved C.
Those methods, initial scr, erase, stuff like that, are those all void returns?
Yeah. Yeah. Well, we could look it up, but we don't need the return values. That's what I'm saying. Actually, init screen does have a return value. You just don't need it.
No lie, maybe I'm just being an idiot. I really feel like this is going to be quite easy.
No, I did the hard work for you.
Yeah, that is correct.
Okay.
I was
Yeah,
more going to ask, how do we initialize something like a double in assembly?
there you go. The challenges is figuring out how to initialize a double in assembly. The figuring out how to do floating point addition, floating point division. Now, there is no instruction for sign, so you're actually going to just call the C runtime library to compute the sign for you.
Also, why don't we ever have to include anything in assembly? They just all seem to magically be there.
That's a really good question. And I think it's worth digressing to answer that completely. Okay.
I did notice that too. Thank you for asking that, because I was confused about that.
Yeah. Now, what is it that you get from an include file? We're talking about a function like puts.
Wait, you only get definitions.
You get all the code in the header file, correct?
No, you only get the definitions.
You get the signature.
So I guess you don't need it because GCC will implicitly link with the actual binaries.
Right. So the signature, you're on the right track, Cephas. The signature is an aid to the compiler in your high-level language. So the signature is giving you the name of the function, and it's giving you the arguments and the returns. But in assembly language, you have to know those things. So there's actually nothing that you need from an include file. You have to know these things on your own. In other words, you look them up with the man pages, that sort of thing. So in assembly language, you have to know the name, and you have to know all of these two to decide register use. All of this is done for you by the compiler when you're using C and C++.
So when you call some function named sign, the linker has to know where that is, where the actual executable
Right.
linked library, whatever the jazz they call it on Linux is.
Correct. Now, let's go into a deep dive on that. We started discussing this very topic in like day 1, day 2 of the class, where we talked about what it is to compile your code. So your code goes into the preprocessor, and your code changed comes out. Then your code changed goes into the compiler, and assembly language comes out. The assembly language goes into the assembler, and object code comes out. Object code goes into the linker, and an executable comes out. So let's talk about the role of the linker. So in this program, we want to make use of sign, right? So here is my, let's say, my code as an object file plus the C runtime library equals the executable. Now, the implementation of sign is in there. So when you have the execution units, I'm sorry, the compilation units. So here's main.obj, and it says, I have, well, I have main. I want sign. Here is the C runtime library, and I have sign. Actually, it's not the C runtime library, it's the math library. I lied.
So
Okay.
how does it handle namespace collision? What if I include 2 libraries that happen to have something called sign?
Well, then that's handled by the, in C, it could be done as long as only one of them is used in an in a compilation unit. But in C++, that's what you have namespaces for. So it's all handled in the higher level language.
So in assembly, the linker would just yell at you?
Well, yeah, you'd have to do some other magic. Okay, so let me finish this up though. So the linker, that's the job of the linker. It goes through this table of contents, TOC, table of contents for each compilation unit. And it just makes sure that all of the wants are matched up with all of the haves. Okay? Let's look at the word extern. So if you say extern foo, actually it would be extern int foo. And that was in here in one of your compilation units. What that says is I want foo. And one of your other compilation units will have to supply it, or the program won't link. Okay?
Also, when it's compiled to an object file, so the object file somehow has to have these names somewhere. in there.
Mm-hmm. Right. So what is the difference between an object file and an executable? The executable has had all of its symbols reconciled, whereas an object file may be calling out to a symbol that's not contained in the object file itself. So an object file is machine code, machine language, but it's not a complete, pretty present in a box, packaged executable. It's incomplete. Okay? All right, so as I was mentioning, the challenging parts of the program are being able to initialize that and to be able to use floating point division and floating point multiplication and addition. Okay, so that's the point of the project. Any questions about the project?
Phase and theta are just variables within your program. Yeah.
Mm-hmm. Mm-hmm. Right. Yeah, the
Thought so.
phase is what's used to, what did I use phase for?
Phase animates it?
Yeah, phase animates it. So let's see. The increment is 2 pi divided by the number of columns on your screen. Yeah, let's see, is theta changed anywhere? Oh yeah, okay. So theta is the angle going across the line, but the angle of the first column is phase. That's how this works. So theta is being, across one line, theta is being incremented, but from frame to frame, phase is being incremented. Okay. So that's it. That's all you got to do. Let's look at the spec. See, that's not there. That I don't need. That I don't need. What is this? Who knows? God damn Zoom. I can't find anything. All right, so here's the spec. If you don't have end curses, then this is how you install it. Okay, here's a complete description of what's going on under the hood. You do have to link with the math library, so I was correct. It's not in the C runtime, it's in the math library. And you have to link with curses. You can link with curses or end curses. So just do end curses. It's the same library. Curses is a historical name. You may be wondering, what does curses do? And what it does is, let me go here. So imagine, if you will, it's a long time ago, and you are connected to your computer via a 300 baud modem. Okay, So 300 baud is roughly just about 30 characters per second. So you're able to receive 30 characters per second from the computer. Now your screen is 80 by 24 characters. What does that multiply out to? I think 9,600, right? Just recollection. 80 by 24. Anybody who's got a calculator?
80 times
1920.
24. Computer, 80 times 24.
1920.
1920. Okay.
19.
1920.
Shut up, Alexa. I'm
Okay.
better than you.
Right. Okay, so 9,600. So what's divided by 30?
Computer, 1920 divided by 30.
64. I'm better.
1,220 divided by 30 is 64.
64.
All right, it's 64 seconds to fill in every character on your terminal. So if you want a to refresh, you're in VI and you want to refresh the screen, it could take as long as 64 seconds to update the screen once. That was before curses. So what curses does is it creates ASCII buffers. It's a form of double buffering for your, like in your video games. So ASCII buffers that are both width times height, usually 80 by 24 to start out with, but it could be bigger. And there's 2 of them. And the notion of double buffering is that the buffer that you're writing into is not the one that you're showing. When you have completed writing to the hidden buffer, you make that one the visible buffer and start writing into the previously shown buffer, which is now hidden. And so this is the buffer you're showing, and this is the buffer you're writing into. And then when the refresh happens, you flip. So you start writing into this one, you're showing that one. The refresh happens, you're showing this one, and you're writing into that one. Okay, that's double buffering. So what
Doesn't it
curses-
still take the same amount of time to actually update the refresh?
No, because, and it was the sentence I was about to utter, is what curses does is it compares the current buffer with the next buffer, and then it emits only the characters that have to change. So here, let me, oh, that's still here. There exists a ANSI escape sequences. That's what it's called, ANSI escape sequences, which would be the escape. Here's the escape sequences necessary to move the cursor. Escape, left bracket, 1 semicolon 1 H. That will call, if you print that to your screen, that will move your cursor to the first row, first column. And then you can erase the screen, for example. So escape bracket 1J. That J looks a lot like that's a J, not a bracket. This is the escape sequence to clear your screen. So by sending out the escape sequences to carefully position the cursor, then the screen would only update exactly what it needs to show the next, the desired next screen.
So when
Any
you
questions?
say, yeah, so when you say send it out, send it to where?
To the terminal.
Oh, okay.
See, we're back in the days when your screen was not built into your computer. There was a wire, serial port that connected the computer to the terminal. There was a tiny amount of logic on the terminal, enough logic to interpret the escape codes. That's about it.
So you would like load that up into X0 per se and then puts it out, right?
Right. Right. Well, no, you wouldn't want to use puts because that would end with a new line and that would screw you up.
So it'd just be printf, but how would you format the string? What would it be? Percent %S?
You want to do this, don't you? You want to do this. You want to do this right now. Is this what you want to do now? Okay, let's do it
I
now.
mean, we don't have to.
All right. All right. So I'm wondering what happened to my, oh, did I? Why don't I just kill this terminal? I think I've blown it up. Okay. So, all right, I'm digressing because, oh, there's all sorts of chat. Yeah, nice haircut. Who is it that got the nice haircut?
That was two's compliment.
Okay. All right, so you wanted to try out these escape codes. So Visual Studio, and let me show that. And share screen. Okay. This is going to be fun. Here, watch this. I'm going to run VI inside code. So yeah, we'll just do it like this. While true, printf and let's see, how do you do?
Couldn't you use echo
Yeah.
from the terminal?
Too much work.
Yeah, but I don't want to.
Seems like more work.
But this is what Jordan wanted.
Yes.
Fair.
I'm the captain now. I choose what we learn.
Are you missing a closed bracket with the one semicolon 1?
No, that's the way the escape codes work. So it's just the one left bracket. So this is boy, it's been so long since I did this. I used octal. Nobody ever uses octal, but that's the escape character in octal. And I think putting a 0 in front of it does the right thing. That makes it octal. All right, so hello, and it's frozen. It just couldn't deal with my magnificence. Okay. Okay. Oh, well, it should be called printf, right? There it is. Woo-hoo. Whose idea was it for me to do this? God
Cephas,
damn it, Jordan.
Just use the terminal.
I just want to know how to execute the escape commands. I didn't think it'd be this difficult.
Okay, so where is the hello? Do you see it? Where's the cursor now?
Top left, where Kovalowitz used to be.
Right. So here, watch. I'll run it again. And boom, cursor's back up there. Okay, Jordan, there you go. And that is how relatively modern computing came to computers with these escape sequences.
Did it
Okay.
take that long back then, or was it faster?
What?
Never mind. It was a bad joke.
Yeah. Well, by the way,
So a joke for you.
my 1100, CSC 1100, we've been using escape sequences all term. So they're way ahead of you guys. Okay.
What is that CAT call? Where with Fusi, what is that? What is that call? I know it
What?
gives code. The CAT foo.c.
Okay. Would it surprise you to learn that you can find out what that means by saying man cat?
Oh, good point. Because they have all that built in.
Right.
Catnate and print files. Okay, thank you.
Yeah. Now, it does concern me that the command is named man. I think it should be called person now because, you know, man is sexist. So,
Ain't
but
that
it doesn't
joke
work now.
too?
Person cat doesn't work.
Linux is sexist, apparently.
Yeah. So love not found. Okay. All right. So questions about what we've gone over? Anybody? And then I'm going to say it again. A number of people have not turned in projects. That's a sure way to get an F. You are welcome to go ahead and turn those in. Turn in your work. Okay. Do you have any questions about project 3 or 4?
I just realized I forgot to implement the line is longer than 4,000 bytes thingies.
Mm-hmm.
I'll have to resubmit.
Okay, you can resubmit. Now here's something that bothers me. Schoology will tell me that someone resubmitted, but there's no way to find out who. So if you're going to resubmit something, you have to email me, letting me know that you resubmitted. Okay? So if your grade is not where you want it to be, then you have the opportunity to hand in the work that you might be missing. Okay? All right, we have, do we have a midterm in this class?
We don't have to.
No, we have to do whatever the, the
It looks like,
syllabus says.
based on the organization for the grades, it looks like that's P4.
Well, let's look at the syllabus. And I'll project the syllabus. Okay. Midterm, there is one. Okay. So you're going to have a midterm soon. And my expectation is that the midterm will be the 23rd. Let me look at this one. Your midterm will be on the 23rd. It'll be in class. It'll be multiple choice. It will not be a big hairy deal.
Will it be up through floating point, what we're doing this week?
Absolutely.
Okay.
Now we'll have a review day. So that'll be on the 18th. But keep in mind, the way I do review days is you have to lead it. I'm not going to come up with things to review, right? You have to introspect, figure out what you might be weak in, and then you have to ask questions. Okay. All right. Well, that is, let me check my agenda that I keep for myself. Whoops, you're not supposed to see that. Stop sharing. That's too much to share. My agenda for today, yep, we have completed the work for today. So if you have a question, ask it now. Otherwise, we can end early. I'm looking at the attendees and I'm sad that there are students missing.
Yeah, I keep on like thinking, is there always less and less people in this call every single day?
Eventually, it'll just be you, Thomas.
Mm-hmm.
That'd be boring.
All right.
We're all in your head.
As if you weren't already.
So let me understand this right. This is a required class for the major, and you can't move on in the major. You can't graduate without this class. Why wouldn't you be here?
Probably because they know that you record the videos and post them on the internet.
Okay, I suppose that's possible.
Unfortunately, I do agree with that idea, and
I'd say maybe if they're behind, or if they're stuck and don't know what to say or what to ask, it might be overwhelming. Because I've been in a situation like that before with other classes. So, but I don't know. You know, if they don't reach out, then they don't reach out. You know, it's not your job as the teacher to reach out. If they need help, they should reach out if they need help, you know, so.
Yeah, okay. All right, well, thank you for coming here today, one of the few. And if you have any questions, reach out to me. We have the barbecue on Thursday, 7 to 9 p.m. Cephas. And that's on Thursday. And reach out by email between now and then. You can schedule appointments with me using Google Calendar. All right. Okay, then we can end early.
Thank you. Have a good day.
Thanks. All right.